So, Newton's third law, okay? Very simply, Newton's third law says that every action has an equal and opposite reaction, okay? If I push on a wall, what will the wall do? Push back, okay? It's pretty simple, okay? So all forces act in pairs, okay? Understand what's meant by normal force. We've talked about normal force, but we haven't really gone into what it is, why it's there, okay? So we will be doing that. And then, obviously, understand for every action, there's an equal and opposite reaction. Okay? That's not always obvious. Okay? And that's the weird thing about Newton's third law, is that people don't always understand that there are forces acting in pairs. Okay? But it's why certain things happen. Like, for example, if you ever shopped at like Costco, you have those people to check your receipt at the door, okay, or check your card when you come in, make sure you're a member. Okay? You ever notice that they're always standing on an anti-fatigue mat? Okay, they've always got one of those mats, those kind of foam things on the floor that they're standing on. Because if you were standing there doing that job all day, okay, on a concrete floor, your feet and legs would get sore. Because the force of all of your weight is going to be returned directly to the pressure points on your feet. Okay, and that's going to make your feet get tired, it's going to make the muscles in your legs get tired. But if you're standing on something softer, some of that force can be dispersed a little bit around and a little better over the entire surface of your foot, making you have less fatigue in your muscles. Okay, if you sit for a long period of time in your chair, okay, you feel like you got to move around a little bit because you lose circulation to your legs. Okay, because there's a constant pressure. Your weight's pushing you down into the chair is pushing back, okay, and that's creating that force that you feel. Okay? That's also kind of how we know, like if we're sitting down and not looking at a chair, we know when we're there. Okay? Because we can feel the chair pushing on us. Okay? Does that make sense? All right. So that's what we'll be looking at here today. So if you're in a football game like these, these two an offensive and defensive line here, when they crash into each other, okay, there's a lot of forces there. Okay? But they're forces that act in pairs, which is why you generally don't see like one line move the other. They just kind of hit each other, and there's this attrition that just goes on, and they don't really move very much until somebody slips past someone else, right? But they all feel that force, okay? I exert a force on something, it exerts a force back on me, okay? So that's kind of what we're looking at there, okay? It's why if I put a book on a desk, and that's the most common one we've looked at, the gravity pulls it into the desk, but the desk pushes back. If it doesn't do that, then the book falls. Okay, something has to push it back. It's also how, if you've ever blown up a balloon and then let it go, okay, it flies around the room, right? And the reason it does that is because when you put pressure inside the balloon by blowing air into it, the air pushes on the balloon. What does the balloon do? Pushes back on the air. If you release that thing, then that pressure of the air surrounding, okay, is what's going to throw it around the room. Okay? Until, of course, there's not enough pressure for the balloon to push back, and then it'll stop. It's also how rocket engines work. Okay? They all rely on what we call reaction control systems. Okay? That's those little thrusters or little jets that push one way or the other. Okay? All right. Making sense so far? All right. I want you to look at this situation. I'm going to give you a couple minutes here. So this person is in this canoe. They don't have a paddle, so they're literally at the creek without one. Okay? And they're trying to get back to the dock. They're going to run through the canoe and jump off the canoe. I want you to think about whether that gets them there or not. Think about it in your mind, because I know right now you're all drawing a conclusion, but I want you to think about it for a second. Okay, so you look at this situation. How many people think he'll make it to the dock? You're all wrong. But we all imagine this situation. He's running along this canoe. He pushes on the canoe, and the canoe slides out from under him. Does that mean the canoe doesn't push back? The only reason the canoe slides backwards along the surface of the water is because he pushes it. But every action has an equal and opposite reaction. When he pushes on the canoe pushes back. It's totally possible for him to jump out of the canoe. Now, I'm not saying that it's not going to be hard. Okay? It's also directional. If he just pushes straight back against the canoe, okay, then he's not going to get the same kind of thrust forward that he's going to need, okay, because the canoe is going to try and move backwards a little bit, all right? But if he pushes down more than he pushes backwards, it's not just the canoe he's pushing on, it's all the water underneath, okay? So there's going to be less movement of the thing away from him, more movement downwards, and he gets up and over a little more easily. Now, if I had this instead of just a small canoe, I had him like jumping off of a big cruise ship and onto a dock that far away. Would any of you said he wouldn't make it? Everybody would say he would have made it. But you know what? Pushing off that cruise ship would give him just as much push towards the dock as the canoe, because it's about the force he exerts. Right? We all think, oh, bigger mass, he can't move that big boat, so he'll easily be able to jump off because that boat's not going to move. Actually, it will. It'll accelerate too. Not as much, because obviously it's got a much bigger mass. But the force it pushes on him with will be the same as the force that he pushes with. Okay? Every action has an equal and opposite reaction. It's not about the boat, it's about how hard he pushes on it and what direction he pushes on it.
Is he jumping off and he's jumping like more forward? Can you just slide out under him?
That's what I'm saying, but it will, but it doesn't mean it doesn't push on him. It still pushes on him. Oh no, still enough. Yeah. Now, he's got to push downwards. If he runs all the way through this canoe and he's always pushing backwards, yeah, by the time he gets to the end of the canoe will be back here. That wouldn't be good. Okay? What I'm saying is if he runs, it just kind of pushes, and then gets to the end of the canoe and pushes mostly downwards, like this, the canoe pushes with an equal but oppositely directed force. Enough to push him onto the top. Okay? I'm not saying technique isn't important. Technique would certainly be important. Okay? But it should still get him.
Is that like when you have like rocket power, when you push up and then like when they go into space?
Yes, exactly the same thing. Rocket engines work on Newton's third law. The pressure that they exert, the pressure of the gases inside, pushing on the inside of the rocket, is the same as the rocket pushing on them. It's just they're allowed to escape, so it pushes the rocket forward. Okay? Which is also why, as the rocket continues to go, its acceleration actually increases. Its acceleration increases not because the force increases, the force actually decreases. But what's happening as it's spewing out all of that gas, what's happening to the mass of the rocket? It's getting smaller. So rockets accelerate better as they go because they become lighter and lighter. Okay, so that's Newton's third law. Okay, it's the action-reaction law. Okay, every action is an equal opposite reaction. When he pushes on the boat, he gets over onto the dock as a result. Okay, so whenever one body exerts a force on the second body exerts an oppositely directed force of equal magnitude. Okay, this comes into play a lot if you're thinking of maybe as a career choice becoming like a truck driver. Okay, Newton's third law plays into the mechanics of towing a tow vehicle in a massive way. Okay, if I have my trailer attached to my truck and I start trying to accelerate away, my truck doesn't accelerate nearly as well as it does when I'm not attached to my trailer. Okay, the obvious explanation is, well, you've got all that mass behind you, right? And when I pull on that mass, what does it do? It pulls back. Okay, and that's what slows me down. I don't just have the mass of my truck and friction and all that other stuff. I've got all of that acting on the trailer as well. Okay, and even worse than that, when I try to slow down. Okay, when I push on the brakes, my trailer keeps moving forward. Okay, well, hopefully the trailer brakes work, but okay, if they don't work, it tries to move forward and it pushes on my truck, and my truck pushes back, and then we get this bad thing going, and we get sway, and I can be done. Okay, so that sort of makes sense. All right, so let's look at this very simple Newton's third law example. So I have this astronaut, okay, and they're facing a spacecraft like you see here, and they're going to push on the spacecraft. Okay, so it's going to look very much like what I'm going to do here, okay, except the wall's not going to move, right? So if I push on the wall, what's the wall going to do? Okay. Okay, so I push on the wall, and I move backwards. Okay, and most people say, well, yeah, you pushed yourself backwards. No, I didn't. What direction did I push? I pushed that way, but I moved backwards. Okay, I pushed on the wall. I pushed north. Okay, I moved south because the wall pushed me back. So same thing with this astronaut. He's going to push this way, okay, to the right or in a positive direction on the spacecraft, but he's going to accelerate to the left because the spacecraft will exert an oppositely directed force of equal magnitude back on him. All right. So if I want to calculate the acceleration, okay, of the spacecraft, okay, so we want to find the acceleration of both the spacecraft and the astronaut. So the force exerted by the astronaut on the spacecraft is 36 newtons. The mass of the spacecraft is 11,000 kilograms. Okay, F net equals m times a. Which force acting on the spacecraft is?
The space.
The spaceman. The spaceman. Or woman. The astronaut. Okay? So, they're pushing on the spacecraft. Okay? That's the only force, 36 newtons. I know the mass of the spacecraft. I can calculate the acceleration. Okay? So, we're going to have our 36 newtons, positive 36 newtons, divided by 11,000 kilograms. Is that going to accelerate very much? Nope. But it's going to accelerate. Okay? The spacecraft will move slightly away. And this is how all spacecraft are maneuvered. Okay? All the probes that we've sent into the outer solar system, like the New Horizons one that went by Pluto there a couple of years ago, okay? All of that, they do course corrections that are tiny. Okay? They don't use big thrusters. They use really small ones, and they do it well in advance. So the effect of it has a long time to take place. Okay? So the acceleration produced on this spacecraft, okay, is going to be 36 divided by 11,000. Okay, so we're looking at 3.3 times 10 to the minus 3 meters per second squared. Very small. Very. Very. Okay? But it's an acceleration. Still move the spacecraft. Okay? If we're doing this for the astronaut, what force do I use instead? Negative 36 newtons. It's the same magnitude, just opposite direction, and now acting on a smaller mass. Obviously, the astronaut is going to move a lot more than the spacecraft is because they're smaller. Okay? So the acceleration of the astronaut will be negative 36 newtons divided by their mass, 92 kilograms, and we get like 0.3 or something like that instead. Okay? A much greater, 0.39, okay, meters per second squared, a much greater rate of acceleration. Still not huge, but much greater than what the spacecraft experienced. Same force, different accelerations, okay, because of the different masses. Now, is there any new math here? No. There isn't a formula for Newton's third law. Newton's third law relies on the math from Newton's second law. Okay, that's all I used here, right? I use Newton's second law math. Okay, but I just have to remember with Newton's third law that forces act in pairs. Okay, it's just like putting more forces into the free body diagram for a Newton's second law question. Because in the end, all Newton's second law questions, all Newton's third law questions are really just Newton's second law questions, as long as we remember when I do that force, there's a force back. That's really what we have to remember. Okay, so we just explained all of that, and we did that math. So, okay, even just walking, that relies on Newton's third law. Okay, in order for me to propel myself forwards, I need to push backwards. Okay, when I push, okay, I'm trying to push the floor that way. Okay, and the floor pushes me that way. Right? Now, depending on how you walk, you're relying more or less on the friction on the floor. Okay? Have you ever noticed? Watch people walk. Everybody walks different. Okay? Some people, like their head hardly moves, right? When they walk, their head is pretty flat. Okay? Those are the people who push mostly horizontal when they walk. Then there are the people that walk like this. They go up and down a little bit more because they tend to push downwards a little bit more. Okay? So their force is directed backwards and down, so the force the floor exerts back on them is forwards and up. Okay? So they tend to move in a more sinusoidal pattern than a flat one. Okay? If I want to jump, I'm not going to demonstrate that because my knees are too bad, I'm too old. But if I want to jump, which way do I push? Okay. You know what makes you jump? The floor. Okay? Right now I'm not jumping because I'm not pushing on the floor with a greater force than the force of gravity. Okay? But if I want to get ready to jump, I bend my knees and I get ready to exert a force on the floor. Okay? And that force is going to be greater than the force of gravity. And what does the floor have to do? It's got to push back. And when it does that, it's pushing me upwards with a force that's greater than gravity, allowing me to accelerate up off the floor. Okay? That makes sense? You never probably thought about that, but in order to jump, you actually push down. We think we're pushing, but we're not. Okay? We're relying on the floor to push us up. Okay? It's weird, but it's true. Okay. If you become an astronaut and you become separated from your spacecraft, you're dead. Except if you take my advice. Never leave the spacecraft without a big, heavy tool. Okay? No matter what you're doing, take something big and heavy with you, like a big wrench, okay, or a big hammer or something. Okay? And you're not going to smash your faceplate and like pull a woody like we saw, okay, in the Newton's first law lesson. Okay? That's not what it's for. If you get separated from your spacecraft, throw the wrench. Why? Away. Yeah. Okay. If I can get my back to the spacecraft and I've got something big and heavy, if I throw it away from me, when I push on it, what does it do to me? It pushes back. Okay? Give me a small amount of acceleration and get me moving in the other direction. Might be enough. Okay? It might take me a long time, okay? But I might get back because I can produce an acceleration in the right direction.
You're in space and you're going, like, you push back and you're going. Do you, like, never stop since
That's right.
there's no air resistance?
That's right.
Going forever?
Yes. Were you not here the day we watched that video?
I was.
Oh, okay, yeah. So yeah, that's what would happen. So if I have that big heavy wrench, I'm only going to accelerate for how long? For as long as I'm pushing. Okay? As soon as I let go of the wrench, now I'm not exerting a force on the wrench isn't exerting a force on me, my acceleration is over. Hopefully it was enough to give me some velocity in the right direction. Now, some of you might be thinking this, and it's okay, because almost every time I say that, people are like, well, then why would you let go of the wrench? And I just kind of give them that look. If I don't let go of the wrench, that means I have to do what to it? Pull on it. Okay? So I push on the wrench to try to move myself that way. Then I don't let go of the wrench. So I pull on the wrench, and the wrench pulls back, and I just sit there going like this, looking stupid. Hey, not going to go anywhere. Hey, it's going to look like I'm beating the hell out of that wrench. Hey, it's not helping me. Okay, I need to make sure I actually let it go. You have to sacrifice the wrench. Okay, it's going to burn up in the atmosphere. It won't hit anybody. Okay, so you have to throw it. Okay, you have to throw it and let it go. If you hang on to it, you won't go anywhere because you're going to exert a force in the opposite direction to stop the wrench. Okay, now you also notice every time I demonstrate that, I show like kind of a chest pass motion. Okay, why do I do it that way and not like this?
That's when you'd be pulling yourself the other way, like when you swing it back.
Okay, yeah, if I go back this way, I'm going to start, well, that's the problem, is I'll start to rotate. If I throw it like this, I'm exerting a force outside of my center of mass. So when I let go of that wrench and it's kind of on a trajectory like that, it's going to exert a force back on me. I'm going to tumble end over end back towards the ship. I want to kind of put that wrench near my center of mass and go like this so that I move straight backwards. Otherwise, I'll like throw up in my spacesuit, which is fatal, actually. You don't want to puke in your spacesuit. Anyone know why? You'll inhale it. It floats. Okay? If you throw up in zero gravity, it doesn't fall to the ground like it does here. Okay? So it floats in front of you, and if you inhale your vomit, it will burn your lung tissue. And it can kill you. Yeah. Drowning on your own vomit. Right up there on my list of ways I don't want to die. Okay? Drowning in my own vomit. Okay. If you don't have a list of ways you don't want to die, you need to make one. Okay? You have to think about these things. Okay? Like,
How do you?
Quickly.
Like a fold?
I don't know. I just don't want to suffer. Yeah. I don't know. Leave a beautiful corpse. I don't know. I guess that's not possible. So, all right. So does everyone kind of understand how this works here with the walking? Okay. And this is something that's kind of funny if you watch people who've never been around snow and ice before. Okay. Like we used to have exchange students all the time here, like 10 years ago from Brazil. And in the wintertime, it was really fun to watch them. Okay. You and I, we take for granted that we know how to walk when it's slippery. Because we grew up in Canada, we're familiar. Ice is just part of our reality, right? Do you ever notice that you walk a lot differently when it's slick? you pick up your feet and you set them straight back down again. Okay? When you pick up the next one, you set it, right? We all do like this, okay? Because we don't want to exert any lateral forces, because what would we be relying on if we had a lateral force? Friction. That's not there. Then we slip and fall, okay? So we want to walk as vertically as possible as we walk, okay? But when you see people who've never done that before, they walk out on the edge, and they just flip right over, okay? Because they have no experience with that, okay? It's not something they've ever done, okay? But it is a Newton's third law thing, okay? The smaller that frictional force is, the less you have to work against you or with you. All right, now, by this logic, when I walk, what am I doing to the earth? Pushing it. Yeah. If I accelerate this way, the earth accelerates that. I'm Superman. I can reverse the spin of the earth and turn back time and save Lois Lane.
No.
You haven't seen Superman 2 yet. Yeah. Okay. There's also, last year in the Super Bowl, there was this horribly physically inaccurate ad starring Kevin Hart. Okay, where they were trying to make the earth go the other way, so they got everybody to run, and then, you guys haven't seen that one?
Nope.
I'll have to find that one sometime. It's terrible. It's terribly physically inaccurate. Okay, think about how much mass I have, and how much force I'm able to exert. Okay, I know I'm not huge, but okay. I'm not going to be able to exert that much force. Okay, the mass of the earth is that much. That's a lot. 528 with 22 zeros behind it. Kilograms. Am I going to accelerate that mass very much? Even if I got everybody going the same direction, am I going to get much out of that? Okay. We're going to actually do an activity on this later about how if everybody jumped, it could knock the Earth out of orbit.
Weren't they actually in the same spot though?
If I got everybody in the same spot at the same time and got everybody to jump, I still couldn't knock the Earth out of orbit.
But they have the same mass.
You would need
Or
like
more
way
mass.
more, like the entire population of the Earth's, like the entire Earth's human population is nowhere near even a small fraction of that.
Nice.
How do you calculate that number?
A lot of different ways, actually. A lot of it to do with orbital interactions, a lot of it to do with geology. Okay. So, another application. You guys have probably all seen the crazy people who rent those little U-Haul trailers. Okay? Right, the small ones. And then, even though they've got stickers all over them that say maximum speed, 80 kilometers an hour, you see them flying down the Deerfoot at 130 with this thing waving behind them like a kite. Okay? So, the danger with those is that they don't have a powered braking system. Okay? Which makes them a little more dangerous to tow at high speeds. Large trailers that carry mass usually have powered brake systems. Because if I push on my brakes as the tow vehicle, I start to slow down. But Newton's first law says that the trailer behind me keeps going forwards. This is what jackknifes a trailer. Anyone ever seen like a semi-truck? Right? Where the trailer is like right up against the truck. Okay, it's just been folded in half. Okay, that's where that comes from. What that is that they're usually on like a really slippery surface. The truck begins to slow down, but because the trailer usually it's empty when this happens, okay, is not slowing down. It just slides. The wheels lock up. It continues to move at the same speed it moved at before, and it pushes on the back of the truck, pushing the back of the truck outwards, and then the trailer pivots around. And because it's not got any slowing force, it actually tries to pass the truck. Okay, leading to them both ending up in the ditch. All right, so you have to be careful of that. That's the big problem when towing heavy objects with lightweight vehicles, especially when they have no powered braking system. So people drive along at 130 towing these things, and then they slam on the brakes because there's a traffic jam or something, and then they jackknife them. Okay, and they end up going off into the ditch or something like that. Okay, so what U-Haul ended up having to do is put in what they call reaction control braking system. And what it is it's a spring-loaded mechanism in the hitch. So when the hitch goes over the ball, okay, for a trailer, in these U-Haul trailers, there's a spring-loaded mechanism that when the towing vehicle slows down, the trailer pushes against the ball. And then what does the ball do? pushes back, and that compresses the spring in here that is actually attached to the brakes. Okay, so the brakes will apply a little bit when you apply your brakes, even though there's no electric or powered braking system going on. It's just a reaction control brake. It just gives a little extra stability to the trailers, but it only works because of Newton's third law. When the trailer pushes on the truck pushes back on the trailer and applies the brakes that way. That sort of makes sense? All right, so we're going to go over a couple of example problems here. Some of them are fairly easy and some of them are like quite in-depth, but they all come back to Newton's second law. They're still going to work as, sum of all forces and F equals m times a and all of that. Okay, so I want you guys to write this one down, and then we're going to walk through it together. Okay, this is a very typical Newton's third law type of problem. So we have three boxes, A, B, and C, that are positioned as you see in the diagram. They're touching each other. Okay, so they're all in a line. And they're on a horizontal frictionless surface. Okay? An applied force acting on box A causes all of the boxes to accelerate. Okay? If I push on the first box, because it's pushing on the other boxes, they all move. Everyone okay with that idea? Mm-hmm. Okay. So they're all going to accelerate at 1.5 meters per second to the right. We want to calculate the force that box C exerts back onto box B. You probably go, what? They didn't tell me about any forces. They just said the boxes are accelerating. They didn't give me any newtons in here. What am I supposed to do? Okay? Well, I'll look at it. So there's no friction. Okay? No friction acting here. But I know the mass of all the boxes, and I know the acceleration of all the boxes. What can I find? F net. In fact, I can find F net for the whole system. I can find F net for each individual box, because I know each individual box's mass, and I know they're all accelerating at 1.5 meters per second squared. Everyone okay with that idea? Okay. Now, I want to find the force that C exerts back on B. So I want to find that force. What's acting on box C? Force A and B. Well, actually not A, because A is not touching C. Only box B is pushing on box C. You're right, I'm pushing on box A. It's causing all of them to move. But what's causing C to move is B. Okay? So there's a force forwards on box C. Okay? That's the force of box B on C. There's no friction. So if I'm looking at box C and box B pushes on it, box C pushes back on box B with who's going on the force? Everyone follow me there? Okay. The only force acting on C is B. Can I find out what that force is since I know the rate of acceleration for C and C's mass? Yes. Okay. So F net on box C is going to be 5 kilograms times 1.5 meters per second squared. All right. So the force that box C experiences from B, the only force acting on it, is 7.5 newtons. According to Newton's third law, the force that C exerts back on B would be negative 7.5 newtons. Okay. Remember how intuitive lots of those Newton's second law questions were? Newton's third law is worse. Okay. We had to do one calculation here, and it was this times that. Did we have to do a lot of reasoning to get there? Yes. Okay. Why did I choose box C to do this with? Why didn't I choose box B to solve this with? Well, yeah, I don't know a lot of the forces acting on A or B. Okay, box C only had one force acting on it, so it was the easiest to look at. Okay, for box C, there was only one force acting forwards. Okay, if I look at box B, okay, there were two forces acting on B. the force of A acting on B, and the force of C back on B. I didn't have enough information to calculate all of those forces, so I couldn't do it. Okay? Similarly with A. Okay? I've got the force of the hand pushing forwards on A, and then I've got the force of B acting back on it. And I couldn't calculate either one of those forces. Because C only had one force acting on it, that force was the net force. And I could go M times A to get it. Okay? Other ones, I wouldn't know enough forces to do sum of all forces with. So I picked the simplest one. Okay, tricky? A little bit. All right, so same example. Okay, so for the situation in the previous example, calculate the force that box B exerts on box A. Now, remember that we did calculate another force here. Okay, we calculated that C is pushing on B with how many newtons? Right, negative 7.5. So here's what you're going to want to do. Okay, you're going to want to calculate this using box B. Okay, use box B to solve for the force that B exerts on A. Okay, your first step is draw a free body diagram for all the forces acting on box B. I'm going to give you a couple minutes on that. Okay, so let's start out with what forces are acting on box B. What's pushing it this way? Box A. Yeah. So we'll call that the force of A on B. That's the force pushing box B to the right. Okay. What's pushing box B to the left? Right. Did we calculate that force? Mm-hmm. Yeah, it's 7.5 newtons. And we calculated that in the last question. Still applies. Same situation. Now, obviously, if it's going to accelerate to the right at 1.5 meters per second squared, the force that A exerts on B is bigger or smaller than the one C exerts back? Bigger. Yeah. So there's a net force here, right? Mm-hmm. Can I calculate it? Mm-hmm. Yeah. I can calculate the net force on B by going mass of B, 10, times the acceleration, which they told us in the last question was 1.5 meters per second squared. So the net force acting on box B is 15 newtons. Okay? And that's positive. And there's only two forces that add up to that, and I know one of them. Okay, so I know that that's true. Those two forces add up to positive 15 newtons. All right, so if I want to calculate this force that I don't know, what do I have to do with this force? Subtract it over to the other side. All right, so the force of A on B equals 15, positive 15, minus negative 7.5. And we only have two significant figures here, I think, but it's obviously going to be 22.5 newtons, or 23 newtons, to the right. Okay, so this force has to be 22.5, 23 newtons to the right. Everybody okay with what I did? Was that really just a Newton's second law problem? Right? I did a mass times acceleration calculation. I did a sum of all forces calculation. That's all I did. Okay? I did a Newton's second law calculation to solve a Newton's third law problem. The thing that I needed Newton's third law for was to get this force. Okay? I needed it to get that force. Okay, question? Yes. Okay, try this one. So I got two boxes now instead of three. Two boxes, and they're made of identical material but have different masses. They're placed next to each other on a horizontal rough surface. So now there's going to be friction. Okay, an applied force acting on box A causes both boxes to accelerate at 2.6 meters per second squared to the right. So I have an acceleration and I have masses. Can I calculate net forces on both the system and the individual parts? Okay. If the magnitude of the force of friction on box B is 28.3 newtons, calculate the force exerted by box B on box A. Okay, trying to find the force that B exerts on A, given this situation. What's counterintuitive about this question is which box you use to solve this. Okay, so let's have a look at this one. They want to know in this question the force exerted by box B on box A. Now, that's one of the forces in this system. Is it equal to another force in this system? If they want to find out how hard B pushes on A, that's going to be equal to how hard A pushes on B. So those two forces are equal. I might be able to find one of them, but I won't be able to find them using like both boxes. Okay, I'm going to have to choose a box here that will give me enough information to solve for that. Okay, that's what I have to figure out first, is which box am I going to have to use. If I'm looking at box A, which has a mass of 6.5 kilograms, how many forces are acting on that box? 3. There are 3 forces acting on that box. There is the force of the hand, okay, so the pushing force, we'll just call that force applied, okay, pushing it that way. There's the force of box B on box A, and what else? Friction. Did they ever tell me what the force of friction on box A is? They don't. So I don't know this force, and I don't know this force. There is no way for me to calculate this force using box A, because I can't use sum of all forces. I only know one out of the 3. Sure, I could calculate the net force. I could go 6.5 times 2.6, but I still have 2 forces in there that I don't know. So I can't use box A because I just don't have enough information to use it. So let's have a look at box B then. Maybe I have enough information for it. Okay? All right, how many forces are acting on box B? 2. There are 2 forces acting on box B. That one, which is the one I'm supposed to find. I'm supposed to find the force that B exerts back on A, but it's equal to that one. Okay? And then what's pulling back? Friction. And they told me that. It's 28.3 newtons. So they gave me that piece of information about box B that they didn't give me about box A. All right, so box B is 8.5 kilograms. Okay? I can calculate the force net acting on this box. Everyone okay with that? Okay, so I'm going to do F net equals M times A. So that'll be 8.5 times 2.6. All right, so we got 22.1 newtons of net force acting on box B. That 22.1 newtons, which is positive or forwards, equals negative 28.3 force of friction plus the force of A on B. Everyone all right with that? Just doing a sum of all forces calculation here. Can I calculate the force that A exerts on B? I'm going to do that. Okay, so I'm going to have 22.1 minus negative 28.3, okay, which should give me 50.4. Yeah. Okay, so 50.4 newtons is the force A exerts on B, and that's positive. What did they want me to find? Okay, what do I do to that number? Yeah, make it negative, right? Because the force that B exerts back on A, according to Newton's third law, is equal, but opposite. The opposite of positive is negative. Okay? The force that B exerts back on A is 50.4 newtons. It's very convoluted. Okay? The reasoning is convoluted. The math is really straightforward. Okay? Run away with that one. Okay, I want you guys to try this one. It's very similar to one we did earlier. I've got 2 logs attached by chains and then attached to a team of horses. Okay, so these horses are pulling these logs through the forest. Okay, they give us the mass of the logs. Okay, they give us some of the forces, and what you have to calculate here is the acceleration of the logs, and in part B, the force exerted by log B on log A. So start out with, draw a picture of the situation. Logs connected together. See if you need to isolate logs to do this. There's some parts of it you need to do together because it's a system, okay, stuff like that. All right, so I'll give you, A should be pretty easy. You're just calculating the acceleration. That's really just a Newton's second law problem. Okay, really only becomes a Newton's third law issue when you get to B. So I'll give you a few minutes on that one and see how you do, and then we'll go over it. Okay, let's look at just the first part here for right now. So we've got two logs, okay? Log B, which is 250 kilograms, attached to log A, which is 150 kilograms, which is attached to the horses. Okay? So the horses, they tell us, can pull with 2,600 newtons worth of force. Okay? And they're saying that friction is resisting with 2,400 newtons on the whole system. Not on one individual log, but on the whole system. So really, what I have here is 400 kilograms being pulled this way by 2,600 newtons, okay, and resisted this way by 2,400 newtons. Everybody okay with that? Okay. This diagram here is also still true. I just don't know the individual forces acting on each log. Okay, but as a system, this is what's true. Can I calculate the net force?
Yeah.
How much is it? 200 newtons forward. Okay, and the mass is 400 kilograms. So, all right, if we've got net force here, okay, and we're trying to find the acceleration, acceleration will be F net divided by the mass, 200 newtons divided by 400 kilograms. This whole thing is accelerating at 0.5 meters per second squared in a forward direction. Okay. This was a simple Newton's second law problem. Okay? You wouldn't have batted an eyelash about that last week. Because today, because I throw Newton's third law at you, it's easy to forget things. Okay? This is just a system question. Now, for part B, you have to do what we've been doing with those box questions. Now I've got to split it up. I've got to look at individual logs here and isolate the forces. Draw free body diagrams for each log in order to figure out what force they're asking you for. And that force is, if the force of friction on log A is 900 newtons, calculate the force exerted by log B on log A. Okay? You can actually do this with either log. Log A is probably the shortest. They're about equally difficult, okay? But log A would be a little shorter. Give you a few minutes on that. Let's look at first log A. Okay, so if I'm looking at log A, it's 150 kilograms. The horses are directly attached to it. They're pulling with how much force? 2,600 newtons. Okay. They also tell me that there's 900 newtons worth of friction acting on log A. Which way does that act? Backwards. What else is pulling on log A? Log B. I mean, think about it. If you were those horses and there wasn't a second log, this would be a lot easier, right? Because there'd be one less force to pull on. Okay, one less log. Okay, so there's still this backwards force here, the force of log B on log A. And that's what they want us to find, isn't it? The force of log B on log A. Well, can I find the net force acting on log A?
Yeah.
Yes, I can. Because in the first part of this question, they asked me to calculate the acceleration of the system. And all parts of the system accelerate at the same rate as the system as a whole. So I can calculate the net force acting on this 150 kilograms by just going F net equals M times A. 150 times 0.5 is 75 newtons. Okay? Everybody all right with that? All right, so I've got 75 newtons worth of net force acting on log A. Okay? So that's going to mean, sum of all forces wise, that F net equals the force of friction plus the force of the horses plus the force of B on A. I know 3 out of the 4 of those now. Can I calculate the one I don't have?
Yeah.
Yes. All right, so I'm going to bring these two over to this side. So I'll have F net minus the force of the horses minus the force of friction equals force of B on A. All right, so that's going to mean 75 newtons minus the force of the horses, 2,600. That's a positive force. Okay, minus the force of friction, which is backwards, so it's negative, and it's 900, right? Equals force of B on A. Okay, so I'm going to have 75 minus 2,600 minus negative 900. That gives me negative 1,625 newtons. Now, I only have 3 significant figures here, so I have to round that to negative 1.63 times 10 to the 3 newtons. Okay, everybody follow what I did there? Right? All we had to remember, okay, was a couple of Newton's second law things and sum of all forces stuff. Okay, really nothing we haven't done a bunch of times before. The other way to have done this would have been to use box B. I could have used box B because I could calculate the force of friction acting on it. There was 2,400 newtons worth of friction on the whole system. Okay, they told me that at the beginning. 900 of that was on box or log A. That means the rest of it was on log B. So this could have been 1,500 newtons, and then you would have had the force of A on B, which is the same as the force of B on A. You could have found it that way. Okay. Either way would have worked. It comes out the same number regardless of right? Because of Newton's third law, every action has an equal and opposite reaction. Okay. So it's a little bit confusing. They seem like it. Okay, they do. They seem like it. But in the end, they're not any different than any of the ones you've done on Newton's second law. Okay, you just have to peer more deeply into the system itself to find those action-reaction type forces. Okay, so rather than go through some of those, I want to talk about the next thing in line here, which is friction. Okay, the reason we haven't talked about friction yet is because it depends on Newton's third law, right? And it depends on Newton's third law in a very simple way. Okay, if I try to move this desk with Cale sitting, is that going to be easier or harder than if he's not in it? Okay, why is it going to be harder with him in it? Okay, there's more mass, and because there's more mass, there's going to be more friction. Okay, and it's not necessarily because of the mass, it's because of what the mass does. So if I have a box sitting on a surface, okay, gravity pulls it into the surface. Okay, and then what does the surface do? It pushes it back up with an equal and opposite force. Okay? If I increase the mass, I increase the force of gravity, and thus I increase the normal force. Everybody okay with that? Yeah. Okay. Now, if I wanted to move this desk with Cale in it, are there some ways I could reduce the effect of his mass? How would I try and move the desk? Actually, pushing would make it worse. Pull. Would I pull straight this way? Yeah, slightly up. Okay? If I lift the desk slightly, I'm not going to do, so I'll throw my back up. Okay? Okay? If I lift the desk slightly, I take some of the weight of Cale and his desk off of the floor, because now I'm holding part of it. Okay? If I reduce some of that weight from being against the floor, then I would reduce this force. Agreed? Mm-hmm. Okay. The force of friction relies on two things. How sticky the two surfaces are, and how hard they're being pushed together, the normal force. Okay, so as an example, if I just hold this marker against the board very, very lightly, it's easy to move it back and forth. Is there friction there? Slightly. Slightly, you can hear it, right? Okay, if I push that into the board, it's a lot harder to move it. Why? I didn't increase the mass, it's still the same marker.
Normal force.
But I increased the normal force, right? When I was just barely holding it against there, I didn't push very hard against the board, and the board didn't push very hard, okay? But as soon as I push harder, okay, then there's more friction. Like, even with just my hand here, right? If I don't push very hard, I can move my hand back and forth really easily. If I lean into the wall, my hand doesn't move at all, okay? It's not because there's more, it's not because the surfaces got stickier. It's just because I pushed them together harder, okay? That sort of makes sense? It's kind of how the wheel works. Yeah, okay? We reduce the amount of friction if we reduce the normal force, okay? The other thing that friction relies on is what we call mu, or the coefficient of friction. There's a coefficient of friction for the interaction between basically any two surfaces. Coefficient of friction can be really high, can be really low, depending on the situation. Teflon against ice would have an incredibly low mu, or an incredibly low coefficient of friction. Those two surfaces are both very slippery. If I push them together, they slide easily past one another because their surfaces are very smooth. Okay? If I put rubber against asphalt, the coefficient of friction there is going to be very high. The surfaces are much different. Okay? And as a result, they do not slide past each other easily and have a very high coefficient of friction. Okay? And that's what we want if we're trying to gain traction. Okay? That's why we typically make the soles of shoes and the tires for cars out of rubber. Okay? Now, can that work for us and against us? Yeah. Okay? Having a high coefficient of friction is great for starting, stopping. When you're rolling, it actually works against you a little bit. Okay? That's why car tires are designed in a way that has like treads. Okay? Tread patterns help to radiate heat. They help to increase friction in different situations, but they also work to reduce rolling friction. Okay? Reducing rolling friction means the car travels more efficiently and less energy from the engine is used to overcome friction. Okay? It's also why we make things aerodynamic. If you drive a block down the road, okay, there's a lot of friction there because a block is not a very aerodynamic shape. Okay? And so we use more energy to move it through the air than we would something more streamlined, because the air goes past it more easily. Angled surfaces, okay? Remember that friction, including air resistance, relies on how hard something is pushed into a surface. If this is a square surface going through the air, okay, the force exerted back is a lot bigger than if I do this. As soon as I streamline that surface, I've got a force coming in like this, but the force of it hitting there is this way. It only has a much smaller component backwards. So I reduce the amount of friction by angling that surface. That sort of makes sense? Okay. Same is true, I don't know if you guys have ever seen this, but like a semi-truck carrying a load of pipe. Okay. What do they do to the ends of the pipes? They block them off. That seems counterintuitive. Wouldn't it be better to let the air go through the pipes? Actually, it's not. It's actually way less efficient to let the air go through the pipe. Because once the air goes into the pipe, it doesn't go straight through it. It interacts with the entire interior surface of the pipe, changing the direction of airflow within the pipe. Now the air interacts all the way along the entire length of the pipe internally, changing its direction, creating all kinds of resistance forces. It's actually better to cap the pipes so that the air goes up and over them as opposed to through them. Like going through them is actually less efficient. Straight. Okay? We think, oh, it should just go right through. It's a straight path, except it doesn't. Okay? All right. Everyone okay with that idea there for friction? So two things affect the force of friction, okay? And that is the normal force and the coefficient of friction, how sticky the two surfaces are. Okay, we're going to talk more about that relationship tomorrow. Okay, the coefficient of friction and normal force, that'll be kind of tomorrow's lesson. And then we're going to do a lab to do with friction, okay, hopefully this week. And then we're going to be moving on to work energy theorem. Expect, I'll probably have a date for your unit exam on the board tomorrow. Okay, probably know when we're going to do that by the end of the day tomorrow. Okay. Remember, your Newton lab is due Friday. Right, the 25th?
Yep.
Okay, your Newton assignment, that's the one you got yesterday, due on Monday. Okay, that's what you got coming up. Don't forget about any of it. You still have some time in class, I would suggest you use it to work on your Newton assignment, or your Newton lab report on your phone if you have that, or one or the other, but not packing up and thinking you're done.